a remnant of Chapter 2 to talk about for a few minutes, given that we still have a fair number of econ-inclined people left in the class, right? I think there's like half a dozen still.
One, that's fair.
So there are a few places. I'm going to do lots of physics applications throughout the year, but I'm going to try to do some econ applications as well. And towards the end of this semester, there will actually be a problem that all econ/business type people are required to do, but will be extra credit for everybody else. Just to punish you guys.
What if it's a little second side thing? It's like a second side major that just kind of exists.
Just forget about it for a week.
Alright.
Change your major.
No, I'm not doing this to be punitive. I'm doing this to make you understand both the math and the econ better. And when we get to this stuff later in the semester, I'll remind you. But I do want to try to do some econ applications, and so you might think they're sort of not super deep, and this, what I'm about to do today, isn't, but it's still worth noticing. So I want to do I'll put it in quotes, an economic application of dot product. And those of you who take microeconomics will see this everywhere, even though they don't use much math notation because students are scared of it, but they shouldn't be scared of this. Suppose you have a bunch of commodities, that's the fancy word, but a bunch of things you want to go buy. And you want to buy a certain quantity of each of the various things. So X is going to be a vector, say with n components, and what this vector represents is how many units of each commodity you intend to purchase. So this is called the commodity vector, and I want to buy so many units of item I. So it could be that you're going to make cookies, and you could be buying walnuts and butter and flour and chocolate and sugar and labor. And you want to know, if I want to make a certain recipe, I know I need certain amounts of each of these things. And I want to know how much it's going to cost me. So what information do I need? Prices. So I need a price vector, which tells me how many dollars, or euros, or yen, whatever, each unit of item I costs. So this is going to be dollars per unit for item I. So P sub I is going to be how many dollars a unit of item I costs. Agreed? So I'm going to do the dot product to get the cost. Okay, so that's my lame application, but I'm going to come back to more in a few sections later. So the cost is going to be exactly the dot product of the price vector with the commodity. So once we have some matrices flying around in a few weeks, we're going to see more elaborate things to do with this.
What does that say, dollars per unit?
For item I.
For item
Right, so per pound of butter it's $3, so if item 1 is butter and we have 10 pounds here, I'm still going to need to multiply by 3 to get the cost of buying the 10 pounds of butter. Cookies are bad to do the hour before lunch. I should not be allowed to use cookies. But if I start talking about cost of bribing people to do your homework, that's not good. Okay. All right, so that ends the discussion of dot products. We've done Cauchy-Schwarz, we've done triangle inequality. You all will remember all semester the cosine of theta is given by the dot product of the two vectors divided by the product of their lengths. You shall not forget that. Okay. So we're moving on to do the main concepts in linear algebra at this point, and basically we're going to want to have the notion generalizing lines and planes, which for now I'm going to say through the origin. In R3, and we want to do generalizations of those to Rn. So if you think about R2 or R3, can you name me some properties that lines through the origin or planes through the origin might have?
Zero vector.
So because they go through the origin, the zero vector is always in such a thing.
A vector perpendicular to either the plane or the line.
Well, okay,
Like a normal.
right.
Well, I guess it wouldn't be
So-
unique for if it's going to the origin.
So you're right, and that's one way we'll, later in this chapter, we're going to talk about the notion of normal vectors. And in fact, I'm going to talk about that later today. But that's not an intrinsic property to being in the line or being in the plane. So the first property is that the zero vector is in such a set. So I'm going to list properties that a set should have, and then we're going to give a definition. Yes, sir?
Any scalar multiple of the line or a vector that's on the plane should
Also exists.
So
yeah,
if
should
you
also
take any vector in the set and you scale it,
yeah.
it stays in the set. Okay? So for any vector in the set and scalar c times a vector is also in the set.
If you add the name vector in the set, it'll also.
And for any two vectors in the set, their sum is also in the set. How many of you guys have studied differential equation sum? Does this sound familiar? So, no?
Yes.
All right, Matthias, you had a question.
I don't know if this is just a made-up property, but like if you add, for every vector in the set, there is another vector in the set that you can add it to, and it'll go back to the origin.
Okay, so what's that vector always called?
The additive inverse.
The additive inverse minus v, right? And that, although we haven't, I did say this the first day of class. I think Matt even got me into this. Right, what scalar can I put here that will give me the additive inverse?
Negative one.
Negative 1.
Oh.
So that's following. So 2 is often phrased by saying v is closed under the operation of scalar multiplication. So there's this language of a set being closed under something. That means when you perform that operation, you stay inside the set. And 3 is often rephrased. V is closed under addition. So these properties are fundamental properties, and as I said, they show up in differential equations. If you studied what are called homogeneous linear differential equations, solutions have these same properties. And we will come back to differential equations later in this course as well. So any v that satisfy these conditions is called a subspace of Rn. Any subset v of Rn satisfying 1, 2, and 3 is called a subspace of Rn. And the subspaces are going to be the fundamental building blocks of sets that we look at, that we use to understand linear maps, matrices, and so forth. And these are going to be the things that we're going to use to generalize tangent lines down the road. So my propaganda for the linear algebra was we want to do calculus, so we want best linear approximations. These guys are going to be what gives us the generalization of tangent lines. So you should believe that you care about it even if you don't. Can you give me some examples? Okay, so we've got examples, right? These are subspaces. Can you give me an example where 2 holds but 3 does not? So maybe you want me to call these unexamples. These are not going to be subspaces because I want one criterion to fail. Can you give me an example where 1 holds, 2 holds, but 3 fails? And you don't need to be in 27 dimensions. 2 dimensions will be just fine.
If all you have is the 0 vector.
That works.
That works.
Yeah, actually, I should have commented, if you just take the 0 vector alone, is that a subspace?
Yeah.
Yeah.
You can stretch 0 and it stays 0. You can add 0 to itself, it stays 0. So there is a comment here. The 0 vector forming a set is always a subspace. Okay, let's try again.
2 lines.
2 lines. Like, do I have to do anything special with the lines?
Non-parallel.
No, like just the axes.
Ah, so lines to the origin. What do you think? Is 0 in there?
Yes.
Is it closed under scalar multiplication?
Yeah.
Is it closed under addition?
No.
What happens? If you add somebody in this line and somebody in this line, where do you end up?
Somewhere in between.
Yeah.
In fact, if you take, you're going to have homework next assignment where you play around with this notion, and I'll talk about it probably beforehand. But if you take any vector in this line plus any vector in this line, what do you think you get for your possible answers?
Somewhere in between.
Again, Dan?
Something in between.
Well, but all possible is what I'm asking.
Combination?
It creates an entire
That's a
plane.
word we're about to learn.
It creates an entire plane.
It creates the entire plane, is what I wanted you to see. Right? If it were the axes, then it would be totally obvious to you. Agreed? If you took any vector at all of the form x1, x2 can be taken by taking x1, 0 plus 0, x2. So you have a vector in this line plus a vector in this line giving you an arbitrary vector. Perhaps not so obvious in this picture, but we'll actually prove that later this chapter. Okay, that's an example where 1 and 2 hold, but 3 fails. You know what I'm going to ask next.
For 1
Say again?
Or 1 and 3 hold, but 2 doesn't.
Okay. 1 and 3 hold, 2 doesn't. Sammy?
Like the positive side of like what's normally the x-axis,
Where x.
yeah, just half the,
So you're just
where
saying,
x2 has to be positive.
yeah.
Oh, okay.
you're doing in
Or it
the,
could be either way.
but actually, what, can you do it in the plane and use up more dimensions?
Yeah. You could, as long as one like, as long
Like
as,
this?
yeah.
Take,
It's like a
take the
red
vectors
line.
where x1 is greater than or equal to 0?
Yeah.
Is that,
Yeah.
you guys agree with that?
Yeah.
Is 0 in there? Sure, because I put greater than or equal to. If you take a vector in here and another vector in here and you add them, it still has a positive first coordinate. But what's wrong with the scalars? Negative stuff. Can anybody think of another example? Tony should be able to, but I'm not going to pick on him yet. Nobody has a...
Well, I mean, like an entirely different example, or just like shifting it around?
Entirely different example.
Okay.
I've had classes where people thought of this, but it's not something I would naturally expect you immediately to think of. Does this picture suggest something?
Oh.
If it's only
Integers?
rational.
It's just, yeah, it's just like certain discrete numbers.
That's a great word. Who said discrete? Yeah, that's exactly the right word. Okay. Suppose you take the set of points x1, x2, where both of them are integers. So this is the fancy letter for integers. Matthias, do you speak German?
Yeah.
So you should know why this is a z.
Unfortunately, I don't though.
Well, shame on you.
I know, I'm not a good German.
The German word for number is Zahl,
Oh.
and so it's now in mathematics, the standard notation for the set of integers is coming from the German, which is using a z. Do you agree that the zero vector is in this? Do you agree that it's closed under addition?
Yes, because an integer plus an integer equals an
Yeah, and you could even take a tilted, this thing's called a lattice. You could tilt them and make parallelograms at weird angles, and it would still be an example. But it's not closed under scalar multiplication because
You can do fractions.
we're not, worse than fractions.
Yes.
irrational.
Irrational.
Right, any real number other than an integer, if you scale and multiply, you're not going to stay in this. You could, in fact, I'll throw another letter at you. But this one isn't German. How many of you have ever seen this letter? What does it mean? Rational numbers. Why? So why Q for rational number? Quotient. So this means integers. Oh, that's not going to show up. This means integers, and this means rational numbers. What is this going to? So the picture looks very different. The picture looks like. Basically, it looks like the plane, but it has holes. If you zoom in, as if you had Superman vision, you zoom in, you would see holes where any irrational number would be in either coordinate. So this is not discrete, which is Matthias's word, but it is also full of holes. So this, again, is closed under addition because rational number plus rational number is rational. But if you scale by an irrational, you go out of the set. Okay. Anybody else want to add to our list of unexamples? What are we missing?
The one with the
You didn't want to transform and pass through the order.
Well, let me be specific here. Are 2 and 3 holding?
Yes.
So do you guys think 2 and 3 hold here?
Oh.
No, because
No.
you have like an extra number, just like hanging off. Negative x plus 3.
Well, just think geometrically.
If you have 0 times a vector in it, it won't be contained.
It's not closed under scale. Well, in fact, you don't have to be that arcane about it. If you take the vector to here and you scale it, any scalar multiple other than 1 is going to move you off the line. That's true for every single vector here, right? So it's not closed under scalar multiplication, and in fact, it's not closed under addition either. If you take this vector and you add them, it's not on the line. So 2 and 3 both fail here. Okay, back to the drawing board.
Playing with the hole at 0, maybe?
Playing with a hole at 0.
Just define the subspaces.
So-
Subspace like minus.
It's not gonna hold under addition.
That's not gonna hold though,
Put it in
Because
Both
it's
2 and 3 are going to fail again.
Because you could add the additive inverse. and
Correct.
You could also multiply by 0.
Correct.
Is it impossible to do that? Is there no example?
That's what it's tending to.
What makes you question my integrity like that?
I don't know, I'm too lazy to prove it, but that's my guess.
You're going with the smirk.
Well, but there's no way, there's no
I
way.
mean, if you have to multiply by 0, that has to be in the
I
set.
don't think it does.
Then you need the
Don't think it's-
0 vector.
All right,
What
Philip.
about just the null set, just like
guess so.
nothing at all? Empty set.
So
But
Philip
0
had-
is not a
all right,
member of
You
that.
guys,
It's a null
you guys both get prizes here. So Philip gave a proof that if you took any vector and used property 2, you would get the 0 vector. So what have you actually proved here?
Okay.
You see, Jonathan, how it fits with yours?
But there is no,
Oh, yeah.
other than the null set.
If Philip can find some vector in V, then he's proved that 0 has to be in V by property 2. The problem comes with Jonathan's suggestion. What if there aren't any vectors at all?
You can't add 2 vectors together.
I think that would be true though, right?
What would be true?
It would be a subspace?
It would not be, because it
Well,
would.
because 0 is.
Well-
It would fill that.
No, there is no
properties.
0,
It
that's
would-
part of
it- So as long as there is some vector in V, Philip is correct that 1 follows from 2 and 3. In fact, just from 2. The problem is, did I ever say V had something in it? So this is the kind of game math geeks like to play. It's really insidious, it's horrible, but people like to trap you when you weren't paying attention. So, so the empty set satisfies 2 and 3. Why does it, you might ask?
Because there isn't.
It says for all vectors in V, and there's none.
There's none to check it on, so it holds automatically. It's called vacuously. Cal?
We're operating under the assumption that all vectors at the start are the origin. Is there a reason for that? Is that like just a law of it? Is the way things work?
That's the law that makes us be able to draw pictures for the
Okay.
algebra, yeah.
Okay.
So, some books will phrase this differently. They'll say, any non-empty subset satisfying 2 and 3 is called a subspace. I'm giving you rule 1 because I think it's just an immediate thing to check to decide easily. Right? And it allows you to rule this picture out immediately. So if you can see immediately that your thing doesn't go through 0, you know it's not a subspace. So it's really good for showing things aren't subspaces. Yeah?
So if they say that any non-empty set, like satisfying these conditions, does that mean that an empty set is a subspace or it isn't a subspace?
No, because by my definition, the empty set doesn't satisfy 1.
So, but for their definition where they don't discuss.
Well, no, they say non-empty.
Oh, okay, so it has to be not empty.
Yeah.
Okay.
Can you explain example B again one more time? That
This one?
Yeah, no.
So, yeah, so the suggestion was to look at, this was Sammy's idea, to look at stuff in the right half of the plane. So you agree that it's closed under addition because if I add two vectors that lean over to the right, their sum leans over to the right. What it fails is closure under negative scalar multiplication. If I take this vector and I multiply it by -1, it now has a negative first coordinate, so it's not in the set. So this fails too for negative scalars. Okay, right? Yeah. Okay, other comments? All right, so I've done unexamples. How about some unexamples? So I think I'm going to leave the rules up for us. So we've already discussed this briefly. How would you describe a line through the origin in any dimension? Okay, that'll do it. So for the first example then, pick any vector v and consider, I'll call it script L, is the set of vectors of the form x, let's say, just to specify, in Rn, so that x is some scalar t times v for some scalar t. So this set notation might be new for some of you. This is the set of, that's what the braces are, x is in Rn, and then this double dots, some people will write a vertical line, but I would prefer to write colon. This is the condition that x has to satisfy. So this is where your universe is, and this is the defining condition. Everybody okay on this?
What's that word at the end of the top line?
Consider. You can see I'm going to have to work on my penmanship.
Chalkmanship?
Chalkmanship. You guys certainly don't need practice on your gamesmanship.
What's the L for?
It's just the set.
When you say x is in, or the vector is in r to the n, what is that, does that mean every single different, like r to the 1 or r to the 2, or
So,
what does that mean meant by
and
that?
when we say this, we're imagining n as being some fixed integer, but I'm not
Okay.
specifying what it is.
Okay.
You can picture 2, you can picture 3, but it might be 93. Mm-hmm.
Just to clarify, so L represents the entire line, right? Okay, just one.
Instead of all x's that are of this form.
Okay.
So, of course, Matthias is saying that he thinks it's a line. Would you tend to agree?
Depends on which.
So what does line mean to everybody?
It goes one dimension too, actually. For in one dimension.
You sort of can move arbitrarily with 1 degree of freedom. You can't turn, but you can go as much in one direction or in the opposite direction as you want. So degrees of freedom is a term I'm going to use a lot. There is one, Jonathan specified something that I didn't write on the board. There is one thing that might make this not be a line.
Oh,
It doesn't go through the origin.
If
This is
v-
zero
if
vector.
v is the zero vector.
What if v is just 0? What do you get for L?
0.
Boring. So the idea we should say is whenever v is not the 0 vector, L will be a line. All right, but let's officially check that it satisfies the 3 conditions. This is sort of boring, but let's practice doing it. And you'll have some homework to do, not this week, but next week to do some of these. I think not this week. So let's check that L is a subspace. Does condition 1 hold?
Yes, because we just,
Because
you can have a scalar 0.
takes if t equal to 0, we get x is 0 v is the 0 vector, so 0 is in v, is in L. Okay? 2. So I want to give you, for many of you, this is the first kind of formal math argument you'll be writing, so I want to give you the standard way you want to do this. What are we supposed to show? We're supposed to pick somebody in L, give him a name. What do you want to call him?
Q.
X? Okay. I mean, we said V over there, but I don't care. I don't want to use V because V already got used here. That was unfortunate.
Wait, X.
So let's choose X. What do we have to show?
Scalar times x is also within L.
Right. We must show that Cx is in L for any scalar C. Okay? Oops, scalar. So what does it mean for X to be in L?
X equals TV or some E.
So it's lots of words here. So
It's the
T
same
times
as
C,
C
R,
times T times C.
you're ahead of me, but that's right. So Cx is C times TV,
Which also exists in L, because.
which equals, so by, right, the way you do scalar multiplication, if you scale a multiple, you just do the product of the scalars. You can just check that from the definition. Is this a real number? Is that a scalar? Sure. So this is an L, since CT is again a scalar. Okay? 3. What do I have to do for 3?
Simply add 2x
I
or
have to
y.
take 2 things in my set. So I have to start off by saying choose X and
W.
Y.
Why?
Why?
Why do you make me choose W, or why do you make me choose Y?
W.
Use whatever letters you want, but I'll go with X and Y. Choose X and Y. We must show that
X plus Y.
well,
X is TV and Y is SV. Well,
yeah, so here, by the way, Nick didn't fall in the trap. You have to use different letters. The scalars that go with different X's and Y's will be different, so you can't put a T here and a T here. So
they be the same.
SV for some scalars, T and S. All right, now what?
T plus S
Add them.
is
X plus Y is SV plus TV, which is like T.
So X plus Y is TV plus SV,
We can factor
and
out.
then
which is,
T plus
T
S.
plus S times V.
and
T plus S is some
that's a scalar, so we're in L. Okay, that's the end of the proof. So, again, the idea is get you started writing very basic math proofs, and in a few months you're going to be doing very complicated ones, but you're starting with ones where you just take the definition and you just follow through and just verify that things work. What would be a generalization that you would think of instead of doing a line through the origin? What might you try instead?
plane through the origin.
Plane through the origin. How would you describe a plane?
Oh, 747.
Sorry?
Boeing 747.
Is that before or after it's hijacked?
Well, after.
I wouldn't say
Does it become a
All right.
This is going on the internet.
Could you describe the set of a plane as like L equals like the set where X is part of Rn or it belongs to
Yeah.
Rn, where X, the dot product of X times some vector always equals 0?
I'm going to get to that later. If you're in bigger dimensions, think about R3. And I will take all the vectors perpendicular to this guy. Do you think you're going to get a plane?
Why not?
Yes.
Yeah.
Suppose you're in R4.
No.
So I'm back to this discussion we had a minute ago about lines. When we say plane, other than a Boeing of various descriptions, what do we have in mind? 2 degrees of freedom,
So you can
right?
think of it as-
An ant living on this plane can go in this direction, or it can go in that direction, or it can do a combination, but it doesn't have a 3rd degree of freedom to go in a 3rd completely different direction.
So would you just add 2 vectors?
Yeah, you
and
add
just
2
get-
lines.
Aha. So it would be natural then
Yeah, 'cause you said that before.
to pick
Add all the vectors.
2 vectors that are what, Matthias?
Not the same vector or 0?
Perpendicular.
Not parallel.
Oh,
Yeah.
it's not parallel.
Pick V and W non-parallel. And consider what form vector. What do I do with the V and the W?
Add them.
Scale them and add them.
So here's V and here's W. And what do you want me to do with them?
Scale them and add them.
Scale and add. So if I take any vector that's a scalar multiple of V, I get a line. If I take any vector that's a scalar multiple of W, I get a line. And if I add anything in this line and anything in this line, that's what I want to think of as a plane as being.
So then,
So I want to take some multiple of V plus some multiple of W. Mm-hmm.
Do you have to stipulate that V and W are not 0 still? The 0 vector?
What? Non-parallel got that.
Yeah.
It does? Okay.
0 isn't parallel.
So remember we said 0 was parallel to anybody. So if you have 2 non-parallel vectors, neither of them can be 0.
Okay.
That was one of the bonuses of that definition you picked. Yeah. So do you believe you could follow through the proof?
Yeah.
Is there anybody who has doubts? Who will admit it? Okay. So let's talk through it, but I'm going to write down a slight generalization of this, Russell. But do you see how we would get the 0 vector this way? What would you pick for S and T?
0.
Okay, so you got number 1. Suppose you stretched this by a factor of C. What would you do when you took C times X? You would distribute,
C and then it's still scalar.
and then you would say CS is a scalar and CT is a scalar, so it's of the same form. And then when you would add, you would have 2 such expressions with different S's and T's, but you could combine and regroup. You want me to?
We did the last one.
Okay, so you would take X would be SV, so this is for 3. SV plus TW, and Y would be, let's say, S prime V plus T prime W. So if I add, so I'm going to actually write this out quite pedantically. What do I do now, Russell?
Factor out stuff.
Well,
Combine like terms.
Yeah.
like terms meaning
V.
put the 2 V's together. So you would have how many V's?
S plus S prime.
You see that?
Yeah.
And then T plus T prime W's. So this is again a scalar, this is again a scalar, so it's at the same form. Okay, I'm going to actually write out the argument now in a more general case. So for the end, since this is a new week, let me give you a vocabulary word, and then we'll, actually 2 vocabulary words. So if, so I'm going to give you a definition here. If V1 to Vk are vectors in Rn, and C1 to Ck, so by the way, this is what math people do a lot when they want a whole list and they don't want to write, you can't, you know, K might be 3,256,972. I don't have time to write out all that many numbers. Right, so the notation of using ... means that it continues going up by 1 each time until you get to the end, which is there. Similarly with scalars, the vector that you get by scaling each v by its corresponding c and adding them all. So somebody used this word earlier. Is called
linear combination.
Something, linear combination. Of V1 to Vk. The collection of all such things, got a word. It's written span of V1 to Vk is the set of all linear combinations of V1 to Vk. So this is like taking V and W and spanning the plane with them. That's where the language comes from. So this is the set of all linear combinations of V1 to Vk. What do you think the theorem is going to be?
You can forms a plane.
Create an n-dimensional space with k minus 1.
As long as
vectors span.
A span is a subspace of Rn.
Okay, so let's not worry about parallel, non-parallel at all. Let's just say if you take all possible linear combinations and combine them all, what do you think you get? What?
A subspace.
You get a subspace. So the proposition here, the span of V1 to Vk is a subspace of Rn. We're not going to talk about dimension in any formal way until chapter 4, so I'm not going to try to keep track of dimensions at this point. And it's called the subspace spanned by V1 to Vk. Intuitively, the way to think about this is you think of all possible subspaces that contain these vectors, and this is the smallest one. It's the smallest set you can have that's a subspace that contains these vectors. Like here, right? If I had V and W sitting here in R3, you would build a plane spanned by them, and that would be the smallest subspace. Any subspace that contains V and W has to contain all their linear combinations.
What is k in relation to n, or is that irrelevant?
Not related. Could be bigger, could be smaller. Okay, so I will go through the proof of this tomorrow. It's more of what we just did, but I'll go through and I'll write this all out for you. And then I want to do examples. So you guys have been suggesting this several times today. So another basic prescription of a subspace is take any vector little a, well, let's do capital A, choose capital A in Rn, and consider the vectors in Rn that are orthogonal to capital A. So the picture that you might have in your mind would be, here's a vector A. What vectors are orthogonal to that? That vector is, that vector is, that vector is. You should visualize that you get some sort of plane type thing when you take all the vectors perpendicular to A, unless
A is 0.
A is 0, in which case you get, no, if A is 0, what vectors X satisfy?
You get the whole space. Fitting in this
All.
Not a subspace.
So when A isn't 0, this V is called a hyperplane. So somebody's going to now comment that it's a Boeing on steroids.
Right. It goes really fast.
A hyperplane with normal vector, that's just a fancy way of saying perpendicular A. So we'll talk a lot about such things as we go on through this course. And you will see in mathematics that the word normal is absolutely abused.
Why is it a hyperplane and not just a regular plane?
So hyper, aside from suggesting nervous behavior, suggests that it's in arbitrary dimensions, it's one dimension less than what space you're living in. Don't ask me why, because I don't know. But
Does that say when A equals?
Yeah.
not equal.
Not equal.
Okay, so we will pursue with these ideas tomorrow.